Welcome back to our series on obscure and complicated space science topics. Today we're delving into primordial magnetic fields, PMFs, and their intriguing role in accelerated recombination, a mechanism that might ease one of cosmology's biggest headaches, the Hubble tension. In this talk, we'll explore where these fields come from, how they interact with the early universe plasma, the effects on recombination, supporting simulations and observations as of December 2025, and why this could be a game-changer for resolving cosmological discrepancies. Primordial magnetic fields are hypothesized to have been generated in the very early universe, perhaps during inflation or phase transitions like the electroweak or QCD transitions. Today we observe magnetic fields in galaxies and clusters on the order of micro-Gauss, but their origins are unclear. Could they be amplified from weak primordial seeds via dynamo processes? Those seeds could be primordial, with co-moving strengths constrained to less than about 10 nano-Gauss on megaparsec scales from CMB limits. But even weaker fields can have significant effects in the dense early plasma due to high conductivity. Recombination is the era around 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen, freeing the CMB photons we detect today. In standard cosmology, this process is modeled precisely, but magnetic fields can alter the ionization history. Recent 2025 papers have highlighted PMFs as a promising solution to the Hubble tension. By accelerating recombination through enhanced clumping and heating, PMFs shrink the sound horizon, the distance sound waves traveled before recombination, which in CMB analyses effectively increases the inferred late universe expansion rate, helping align early and local H0 measurements without invoking entirely new particles. How do PMFs originate? During inflation, quantum fluctuations in the electromagnetic field can be stretched to super-horizon scales and amplified by the exponential expansion, producing nearly scale-invariant spectra. Alternative mechanisms include bubble collisions in first-order phase transitions or current generation from helical hypermagnetic fields tied to baryogenesis. These fields then redshift as 1/², where A is the scale factor, decaying on small scales due to viscosity but persisting on large ones. In the pre-recombination universe, the plasma is ionized, highly conductive, and tightly coupled to radiation. Magnetic fields are frozen into the fluid via flux freezing. Lorentz forces provide additional pressure and tension, inducing alpha waves, turbulence, and ambipolar diffusion as neutrals form. Critically, magnetic pressure supports against gravitational collapse on small scales, enhancing density perturbations in baryons relative to dark matter. This excess clumping accelerates recombination because higher densities increase the recombination rate, proportional to density squared. Decaying magnetic turbulence also heats baryons slightly, delaying initial recombination, but ultimately speeding the overall process in models. Fields of 0.1 to 1 nano-Gauss cum-oving can reduce the sound horizon by 5 to 10%, exactly what's needed for Hubble resolution. MHD effects also induce vorticity, potentially observable in CMB curl modes, and Faraday rotation mixing E and B polarization. Helical PMFs are particularly interesting, generating parity-violating signals and linking to baryon asymmetry. State-of-the-art 3D magnetohydrodynamics simulations incorporating full radiation transfer and chemistry track PMF evolution through the recombination era. These show enhanced small-scale power, faster ionization freeze-out, and modified acoustic peaks consistent with Planck while easing H0. 2025 updates include non-linear effects and helical components, predicting detectable EB correlations for future experiments. Observational constraints come from CMB non-Gaussianity, spectral distortions, and gamma-ray blazar halos upper-limiting PMFs, but lower bounds from void observations suggest existence. Synergy with Hubble tension is strong, as PMFs naturally explain observed cosmic magnetism without requiring extreme galactic dynamos. Recent analyses combining ACT 2025 data with blazar constraints narrow viable strength to Hubble resolving range. Challenges include avoiding overproduction of mu distortions or excessive small-scale CMB power, but parameter space remains open. If detected via B modes or rotation measures, PMFs would probe inflationary energy scales directly. Visualize the primordial plasma as a magnetized soup. Field lines tangle, stir turbulence, boost clumps where atoms form faster, shrinking the acoustic scale. Like magnetic stirring hastening a chemical reaction. Upcoming CMB-S4 and Lightbird will test predictions. In conclusion, as of December 18, 2025, primordial magnetic fields provide an elegant, physically motivated way to accelerate recombination and potentially resolve the Hubble tension, while accounting for cosmic magnetism. Ongoing simulations and observations may soon confirm or rule this out. Thank you for joining. Like, subscribe, and comment. Could PMFS be the key? Next, neutron star interiors.